Okay, we're going to talk about the material from lecture 15 about finding areas under normal curves and so on. As always, I want to say that watching videos is not a substitute for reading the book and notes. All right, remember we talked last time about the standard about normal distributions in general. Right? And this is kind of what they look like. The highest point is above the mean, mu. That tells you right where the middle of the curve is. And then the standard deviation controls how wide or narrow the curve is. So if you go out to this point where the curve changes shape, the inflection point, that would be mu plus sigma, one standard deviation to the right of the mu along the x-axis. And over here, of course, would be mu minus sigma, one standard deviation to the left. We also found that we could label this curve, we could label it, say, n of mu and sigma, meaning the normal curve, for the probability density function for a normal distribution with mean mu and standard deviation sigma. And when we want to write that a random variable x has this distribution, we would write this. X and then a little tilde, and then that n of mu sigma thing. That means the random variable x is normally distributed with mean mu and standard deviation sigma. And we saw that if you want the probability, let's say if you have an x that is normally distributed with a mean mu and standard deviation sigma, and you want the probability that a randomly chosen value of this random variable x would lie in some interval, right? Let's say this one right here, then that probability is equal to the area underneath the normal curve, this one right here, and over that interval. This is the probability that a randomly chosen value of the random variable x would be in this interval. That's what a probability density function is for. Okay. First thing we need to talk about today is the standard normal distribution. Right? The standard normal distribution is just the normal distribution with mean 0 and standard deviation 1. So the picture of it would look like this. It's often called actually the z distribution. Right? And this axis, instead of being labeled x, is usually labeled z. If you want a random variable with the standard normal distribution, it's usually called capital Z. And again, what would this mean? Z is a random variable that is normally distributed with mean 0 and standard deviation 1. Okay, sometimes you'll see this as well, lowercase z, as a random variable. But usually capital Z. All right, we want to start finding areas under normal curves, and we're going to start with the standard normal. Before I actually do that, though, let me remind you about intervals and interval notation and say a few things about something we're going to need constantly for the rest of this semester. Remember that if you picture an interval, let's say this is the interval from 1 to 2. If you put open circles when you're graphing this sort of interval, it means you don't include the endpoints, and you would write that interval as 1, 2 with parentheses, or round brackets if you like. If you wanted to include, you want the same interval, but you want to include 1, but still not 2, right? So it would look like this in the picture. You would put a square bracket here and a round bracket at the 2. And you can have square brackets or round brackets on either side. You can also have intervals that look like this. They start somewhere, say at 1, and we'll assume 1 is included here. And they just keep going out to the right forever. You would denote this interval, whether you use a square bracket and a 1 to mean 1 is included, and then infinity for the right-hand endpoint, so to speak. We don't think of infinity, the infinity symbol, as meaning a number. It kind of means a process. You just keep going forever. Of course, you can have the complementary sort of thing. Let's not include it this time, so we get one with a round bracket. We'll say that this is 2, and all real numbers to the left of 2 is what this interval is. And you would write that minus infinity to 2. So you think of minus infinity as being all the way out to the left, and infinity as being all the way out to the right. Now, the reason to bring this up is that when you're computing probabilities, you often want to compute a probability like, let's say, the probability that z is less than 2. So here's 0, here's 1, here's 2, and so on. The probability z is less than 2, that's this area under this is the standard normal curve, of course. That's the area under the standard normal curve, all the area to the left of 2. That is, it's the area under the standard normal curve and over the interval minus infinity to 2. The problem is when you calculate things with a calculator, you can't put in minus infinity, right? That's no good. So what we will use instead when we need a minus infinity, so instead of minus infinity, we use minus 1e99. The e means times 10 to the power of. So this is minus 1 times 10 to the 99th. That's the biggest negative number that your calculator knows about, and much bigger than any negative number we might need. Right, so that is essentially the TI's version of minus infinity. And same thing on the right, instead of infinity or plus infinity, we're going to use just 1e99, and of course that just means 1 times 10 to the 99. All right, let me show you how to enter this on the calculator here. Right. One way you can do it is very straightforward. You can put 10 and then hit the exponent key up here, the power 2 key if you like, and then 99. If I hit enter, you'll see it says 1e99, right? The e stands for exponent. Right? That's 1 times 10 to the 99th. There's a second way you can do this. You can use this EE function that's above the comma key. So I could hit 1 and then second comma to get the EE and put in 99. And that's the same thing. 1e99 means 1 times 10 to the 99th. Right? The EE here above the comma key means enter exponent. Okay. Let me show you how to do this with a few examples. The function we're going to use is a thing called normal CDF. Normal CDF. And the way you use it is, for the standard normal, you just put in the left endpoint and then comma the right endpoint. Right? Left and then right, whatever those are. You'll see examples of it in a second. So suppose I want to find the probability that the z variable is between 1 and 2. Nobody has to tell me, by the way, that the z variable has the standard normal distribution. I just know that because everyone just knows that. Okay, let me just draw a picture here. Right? And another beautiful normal distribution picture. Right? And it's the standard normal, so I know where to put everything. What's the probability that z is between 1 and 2? That's the area right here. It's the area under the standard normal and over the interval from 1 to 2. So I'm going to actually write that. Area over the interval from 1 to 2 and under the z curve. To get that with the TI, you put normal CDF of left endpoint, which is 1, and then the right endpoint, which is 2. Okay, so here it is done. Normal CDF is on the distributions menu, so you would hit That's above the vars key again. Second vars to get to the distributions menu. And then you would go down to normal CDF. That puts that on the screen. And then you hit 1, and then you have to hit the comma key, and then 2, right? And there you go. It's about 0.1359. So this would be about 0.1359. Okay. Let's try another one of these. How about the probability that z is greater than 1.48? Again, a picture. So there we go, 0, 1, 2. 1.48 might be right about there, 1.48. And the probability z is greater than 1.48, well, that corresponds to the area under the normal curve, the standard normal, to the right of 1.48. That is, it's over the interval from 1.48 out to infinity. So this is going to be normal CDF of, well, it starts at 1.48, and right here I'd like to put in infinity, but I can't. So I'm going to use 1e99 in the calculator. So we go second vars to get to normal CDF, 1.48, comma key, and now 1e99. I hope I've punched that in. I can't quite see the screen. Oh, there it is. Yeah. It's about 0.0694, something like that. And let me just do one with the minus infinity part. Let's do the probability that z is less than 1.48. Oh, let's say less than or equal to. Well, we're looking at the same picture as here, right? What is this? 0, 1, 1.48 is about right there. And we'd now be looking at all the area under the standard normal curve to the left of 1.48. So this will be normal CDF of, well, you'd like to put in minus infinity, comma, 1.48, but you can't. So what you put in instead is minus 1e99. So let's do that. Okay, normal CDF. And I'm going to hit minus 1 EE99 and then comma 1.48. Yeah, 0.9306. Close enough. This and this, of course, add up to 1, right? Because these two areas have to add up to 1. Let me take a moment here to say that if I had computed the probability that z is less than 1.48, I'd have gotten exactly the same number. And the reason is that the difference between these two intervals is 1 point, the point 1.48. It's included here and it's not included here. But you remember that the probability that the value of a random variable is any particular number, like 1.48, that probability is 0. So these numbers are exactly the same. Okay. You can use normal CDF to find the area under any normal curve. So suppose you have a random variable with a normal distribution of, let's say, 8, 1.3. That is, this x is normally distributed with mean 8 and standard deviation 1.3. Then to find the probability that, let's say, 7.3 is less than or equal to x is less than or equal to 8.3, you would start just like you do with the standard normal. It'd be normal CDF, and you'd put in the left endpoint and then the right endpoint with a comma in between. So 7.3, comma, 8.3. But now, because it's not the standard normal, you need to put in the mean and then the standard deviation of whatever normal distribution you're working with. In this case, the mean is 8, and the standard deviation is 1.3. So that's how that would be used. I won't punch this one in right now because I'm about to do some others. But that's the idea. All right. Suppose that x is normally distributed with mean 12 and standard deviation 0.3, and that an x value is chosen at random. Then, first of all, what's the probability x is less than or equal to 12? You remember what that actually means, right? That means the probability that if a value of this random variable x is chosen at random, that value would be less than or equal to 12. Okay, so first, let's draw a picture. Okay? So here's the normal curve. What is this normal curve? This is the normal curve with mean 12 and standard deviation 0.3. The mean 12 means this is 12, the point right in the middle here. Right? And let's say this be 12.3 about, and 11.7, and so on. The probability that x is less than or equal to 12, that corresponds to the area to the left of 12 under this normal curve. So it's this area right here. And you can see what it has to be. It has to be 1/2, right? Because 12 is right in the middle, and the total area under the curve is 1. To do it with the calculator, though, you would use normal CDF of, then you'd have to put in the endpoints. What's the left endpoint out here? Right? It's really minus infinity, but you can't write that, so you put in minus 1e99, and then the right-hand endpoint is 12, and then the mean and the standard deviation, so that would be 12 and 0.3. So let's actually do this on the calculator. Right? We would have normal CDF, so minus infinity, so to speak, comma, and then up to 12, comma, and then the mean, 12, and then standard deviation, 0.3. And sure enough, it's 1/2 as far as the calculator can tell, out to, 10 or 12 decimal places. All right. So unsurprisingly, this is exactly 1/2. Okay, how about the probability that x is less than 12.2? Now we're looking at 12.2. That might be maybe right about there, 12.2. Okay, and now we're looking at an area, all this area to the left of 12.2 and under this curve. Right? This will be bigger than 1/2 for sure. And the way we calculate it is just the same. Normal CDF of left-hand endpoint. Well, this is all the area to the left of 12.2, so the left-hand endpoint again is minus 1e99. This time, the right-hand endpoint is 12.2, and the mean and standard deviation haven't changed. So what does this turn out to be? Well, let's actually compute it. Normal CDF minus infinity to 12.2 with mean 12 and standard deviation 0.3. Oh, it's about 0.7475. 0.7475. So the area underneath this normal curve and over the interval from minus infinity up to 12.2 is 0.7475. It's about 3/4. All right. The probability x is between 11.9 and 12.1. That would be normal CDF. Left endpoint, right endpoint, mean, standard deviation. It's that simple. 11.9, 12.1. The mean is 12, and the standard deviation is 0.3. Put it in the calculator. You end up with a number. Let's do it. Normal CDF 11.9, comma 12.1, comma 12, comma 0.3, about 0.2611. Okay, let's do something that's, it looks like a word problem. It almost is a word problem. You'll see what I mean. John measured the actual amount of soda in many 12-ounce bottles and found that it is normally distributed with mean 12 ounces and standard deviation 3/10 of an ounce. If a bottle is chosen at random, then, well, first of all, what's the probability that it contains no more than 12 ounces? All right, the situation here, right, you have bottles of soda, many, many, many bottles of soda, and you consider the amount of soda in the bottles to be normally distributed with mean 12 ounces and standard deviation 0.3 ounces. So these things follow a normal distribution with mean 12 and standard deviation 0.3. If we let x be a random variable, that is the amount of soda in a bottle, right, then x is normally distributed with mean 12 and standard deviation 0.3. Well, that should seem very familiar to you. What's the probability that a randomly chosen bottle then contains no more than 12 ounces? That would be the probability that x is less than or equal to 12. And of course that's 0.5, the area under this curve to the left of 12. What's the probability that a randomly chosen bottle contains less than 12.2 ounces? That's the probability that x is less than 12.2. And again, we've already computed that. This would be normal CDF of minus infinity to 12.2 with mean 12 and standard deviation 0.3. Turns out to be about 0.7475. And finally, what's the probability it contains between 11.9 and 12.1 ounces? That's the same as the probability that x is between those numbers. And that is about 0.2611. All right, that'll do it for lecture 15.